Okay, welcome back. Now we're going to talk about the kinds of covalent bonds. There are two types of covalent bonds, nonpolar bonds and polar bonds. The way that we determine if something is going to have a polar covalent bond or nonpolar covalent bond is by the difference in electronegativity, which I have signified by delta En being electronegativity. Let's start with nonpolar bonds, which I think are the easier ones to understand. In these situations, electrons are evenly shared. So when we talk about a carbon-carbon bond, each carbon puts in a single electron, and those two electrons are evenly distributed between both carbons. They're right in the middle. You get these nonpolar bonds when your difference in electronegativity is less than 0.5, all right? So if we do our subtraction here, carbons 2.5, carbons 2.5, 2.5, and 2.5, the difference is 0. So this is a nonpolar bond. And what we have here is, here's our bond, here's our two electrons in the bond. Those two electrons stay perfectly in between the two carbon atoms. This makes it nonpolar, all right? Here we have hydrogen and carbon bond. The two electrons, again, stay pretty much directly between the hydrogen and carbon. Our difference in electronegativity here is 0.4. Hydrogen's got an electronegativity of 2.1. Carbon's got an electronegativity of 2.5. 2.5 minus 2.1 gives us 0.4. That stands in our area of less than 0.5. All right? Now we're going to move on to the more difficult version, or the more intriguing type of bond that we have. These are polar bonds. And in polar covalent bonds, the electrons are pulled towards one of the atoms, all right? You have to think about what does polar mean? It means something has poles. Well, let's think about things that have poles. Magnets have poles. The Earth has poles. Even some compounds have poles. Poles mean essentially that you have an area of negative and an area of positive, or you have a north and a south, however you want to look at it. But there's two areas that are opposite. When we start talking about compounds, we want to think about things as positive and negative, because that's how we look at the atom. We have negative electrons, we have positive protons. So we can start talking about difference in charge that way. So here we get polar bonds when we have a difference in electronegativity that is greater than or equal to 0.5. So if the difference is 0.5, we consider that a polar bond, all right? So there's three examples I have here. The first is this hydrogen-chlorine bond. All right? When we talk about a single bond, there are two electrons being shared by those two atoms. However, chlorine has an electronegativity of 3.0. Hydrogen has an electronegativity of 2.1. That's a difference of 0.9. That falls into our area of greater than 0.5. Because of that, when hydrogen and chlorine share electrons, those electrons are actually pulled towards the chlorine. All right? Now the charge of both of those electrons is negative. So if you have two negative things getting pulled towards chlorine, that's going to give chlorine a sort of negative feel. And we indicate that with what's called a delta charge. It's a Greek letter. This is the lowercase version of it. So if chlorine gets the electrons pulled towards it and has a delta negative sign, that means hydrogen has to have a delta positive sign. We've now created essentially what is a very, very small, very, very weak magnet. But there's an area of negative and positive. As we move forward, carbon and fluorine, all right? Our difference here, 4.0 for carbon, 4.0 for fluorine, 2.5 for carbon, which gives us a difference of 1.5, still falls within our polar range, all right? This means the electrons are getting pulled towards the fluorine atom. As electrons get pulled towards the fluorine atom, it makes that fluorine feel negative, and we indicate that with this delta minus charge. And then we have the delta plus charge here. And lastly, we have a carbon-oxygen double bond. I know you can't quite see the bottom here, but you'll see where I'm going with this. We have 4 electrons between the carbon and oxygen. The oxygen has an electronegativity of, let's see if we remember oxygen, 3.5. Carbon's 2.5, the difference is 1, falls within our polar bond range, so the electrons are pulled towards oxygen. In doing so, it gives oxygen kind of a negative feel. One other way to indicate this sort of stuff, if we go back to the hydrogen-chlorine bond, is instead of doing delta charges, is just draw arrows with one little addition, which is kind of nice. Which way are those electrons being pulled? They're being pulled towards the chlorine. So we draw an arrow towards chlorine, with the one addition saying that we have the positive end towards the hydrogen. So we just make this what looks sort of like a small plus sign down here. If we did that with a carbon-fluorine bond, it would look similar, as well as the carbon-oxygen bond, we get that arrow. All right? Those are our dipole indications. Dipole, two poles, a positive and a negative. And you're going to see that these are going to be viewed as vector values if you've ever heard of that. And these are going to play a huge role when you move on to polar compounds. You ask yourself, why are we going to talk about polar compounds? The reason we talk about polar compounds is because, well, it's the reason why water and oil don't mix. One is polar, one is non-polar.